Hey, today we'll address a topic that is a bit confusing, the subsequence, and we'll try to make some sense into it. Well, first of all, a subsequence of a given sequence is a sequence by itself. Sounds a little bit confusing, but let's work on it. It is derived by a sequence of indices of the original sequence. Yeah, I know there's a lot of sequences here, but let's understand what we're talking about. So let's start with a first sequence, an arbitrary sequence AN that might have a limit, might not, maybe it's monotone, maybe it's not, with the general terms A1, A2, A3, and so on. And let's add to the mix a new sequence, NK. Now, I wrote NK smaller on purpose because NK is going to represent the indices from the original sequence. Now, NK is a sequence of its own with the general elements N1, N2, N3, and so on. However, in this case, we have constraints. If we understand that NK represents the indices of AN, the values of that sequence have to be integers because they represent indices. NK, for example, can be the following sequence: 1, 2, 3, and so on. It can be a different sequence also. It can be 1, 3, and then maybe 5, 7, 11, and so on. Or 2, 3, 11, 19, and so on. You get the idea. Basically, NK helps us decide which elements from the original sequence are going to be chosen. And to understand it better, let's look at the following example. So let's take the following NK, the sequence of 2, 3, 5, 7, 9, an arbitrary sequence that I chose. Now we create a new sequence, ANK, that is AN1, that's going to be the first element, AN2, the second, and so on and so on. I know it's a little bit confusing, but let's see how it looks like. If we remember that NK represents the indices, then N1, which equals 2, the index 2 creates the new first element, A2. Same, N2 equals 3. That means the second element is A3. If we continue this way, N3 is 5, and that's why the third element would be A5. The next terms would be A7, A9, and so on, depending on NK. NK tells us which indices were chosen. Now that's the idea. Now let's understand it even a little bit better by visualizing the whole process. Let's draw an arbitrary sequence so we can work on it to understand it. If this would be AN, according to our example, the sequence that we created, the subsequence, would be A2, A3, A5, A7, and A9, and so on. This would be a sequence of its own, a subsequence that is derived from the original sequence. But that wouldn't be the only subsequence we can create. We can create many different subsequences. For example, if we choose NK to be the even numbers, 2, 4, 6, 8, and so on, that would be another subsequence of AN. We can do the same by choosing NK to be the odd numbers, 1, 3, 5, 7, and so on. That would be a different subsequence. Basically, every sequence has infinite amount of subsequences we can create from it, and each subsequence would be again a sequence. Now let's look at something interesting about this arbitrary sequence. We can see that it's not a monotone sequence. It's not increasing, it's not decreasing. It goes up and down and up and down. However, the subsequence that is created from the even indices is a sequence that is decreasing. Same way, the odd indices create a sequence that is increasing. And that is interesting, because that shows us that a subsequence doesn't necessarily hold the same properties as the original sequence it was derived from. But there is one property that is really important when it comes to subsequences. And to understand that property, let's recall a sequence that we already know very well, 1 over n, the sequence 1, half, third, and so on. That sequence, not only that we know it, we know that it has a limit. Now let's examine the subsequence that is created by choosing the even indices, a2, a4, a6, and so on. Having it in front of our eyes, we see that that subsequence follows the original sequence. Wherever an goes, also a2n goes. That means that if an has a limit, and we know that 1 over n has a limit, it goes to 0, then the subsequence probably has a limit too. Now let's bring back Cauchy's definition. According to that definition, if L equals 0 is the limit, then if we take an epsilon distance from L, up and down, we can find an index that from that point on, the rest of the elements are within the range that is created between minus epsilon and epsilon. But what we notice here, that the same holds for the subsequence. In that same range, we can also bound the trail of elements from the subsequence. If we take a smaller epsilon, we see that we can still bound the subsequence that again was created from the even indices that is marked by the red dots. But we can take it a step further. Not only the even indices, but also the odd indices and the new subsequence that is created consequently and is denoted by the green dots would also be bounded from a certain point in that range between minus epsilon to epsilon, which means that also that subsequence would have a limit according to Cauchy. And now we understood a very fundamental theorem. If a sequence converges to a limit, any and every subsequence of that sequence would also converge to the same limit. But what happens in the case that a sequence does not converge? Like a sequence we saw before, minus 1 to the n, for example. What can we say about its subsequences? So let's take a look, for example, at the subsequence that is created from the even indices, a2, a4, a6, and so on. That is a constant sequence. It's always 1. If we look at the subsequence that is created from the odd indices, well, that's also a constant sequence, always equals minus 1. So let's focus on the first subsequence we just mentioned, a2, a4, a6, and so on, and mark it with red dots. And let's remember that this subsequence is a sequence. And if we consider the option that that sequence has a limit, then the obvious candidate for that limit would be L equals 1. Implementing Cauchy's definition on that sequence means that we're going to take an epsilon up from L and an epsilon down from L. And what we see here is that all of the elements within this sequence are bounded within this range. And it doesn't matter how small epsilon is, I can always find an element that from that point on, the rest of the elements would be still bounded within this range because it's a constant sequence. And that's enough to prove that L equals 1 is the limit for that subsequence. Now let's look at the odd subsequence. L minus 1 is the obvious candidate for that limit. Define epsilon upwards and epsilon downwards, and we notice the same thing. We can find for any epsilon an index that from that point on all the elements are bounded within. Again, it's easy in this case because the sequence is constant. So to sum it up, we found two sequences that are subsequences of the original sequence, and each one has its own limit. But if we look at the bigger picture, we understand that we have a sequence an that has two limits, 1 and minus 1. They are called partial limits. The limits of its subsequences. And now we understand the idea of partial limits. Now it can get more complicated. Some sequences have more than only two sublimits. For example, the sequence cosine of n pi over 2 has three partial limits, -1, 0, and 1. It has a subsequence that converges to -1, a subsequence that converges to 0, and subsequence that converges to 1. And we can play with it. We can create a sequence that has infinite amount of partial limits. But that would be a topic for a different lesson. So thanks for watching and see you next time.